Students, we have to complete differential equations. The part 1 was in the earlier lecture, and this is about part 2. Here we will discuss about differential equations which are given in homogeneous form or reducible to homogeneous form. Homogeneous form we studied in the previous class, homogeneous differential equation. Next we will come to the topic linear differential equation and its various forms, and Bernoulli's differential equation, which is a form of the differential equation, linear one. And lastly, we will study about orthogonal trajectory. And then you will solve problems, either numerical based or word problem are also there, which we will also discuss in the upcoming lectures. So let us start differential equations part 2. So as we studied in homogeneous differential equation, suppose we have been given dy by dx is equal to a1x plus b1y upon a2x plus b2y. So we can say that this is a homogeneous differential equation because the numerator is also linear, having each term with power 1, and denominator is also linear, having each term with power 1. But if we add a constant c1 here, a constant c2 here, then it is no more a homogeneous function either in the numerator or in the denominator. In that situation, we use reducible to homogeneous form. So first case is that if we have these constants a1 upon a2 is equal to b1 upon b2, then the question is simple. In that case, you don't have to reduce it into homogeneous differential equation. Because what happens if this is the condition, let us assume that this is equal to k, say. So in that case, a1 will be a2k and b1 will be b2k. Now if we substitute these values of a1 and a2 in the numerator, the differential equation dy by dx will become a1 as a2k and b1 as b2k, and the k can be taken outside. So k times a2x plus b2y plus c1 upon a2x plus b2y plus c2. Now here there is a very simple method which we studied in the previous lecture, that this is actually a function of a2x plus b2y. So what you need to do is just substitute a2x plus b2y is equal to t. If you will do this, this whole right hand side will change into k t plus c1 upon t plus c2. So in that situation, this becomes a equation with variable t only. There is no x and y, because a2x plus b2y is also t, and a2x plus b2y here also is equal to t. So kt plus c1 in the numerator and t plus c2 in the denominator. And when you will differentiate that, you can substitute dy by dx by dt by dx in terms of dt by dx. So overall the function will be function of t and x, and it will be variable separable. T will go on one side with dt, and x will be the only term which is dx that will go on the other side, and it will integrate to give you x. So if this is a situation, then you have to approach like this. You don't have to use homogeneous differential equation, reducible to homogeneous differential equation, and that will also not work in this situation. Why it will not work, you will just see. So let us come to the second situation, where we know that a1 upon a2 is not equal to b1 upon b2. These are not equal. In that situation, what we do, we write this small x variable as capital X variable plus a constant h. We will decide what is the value of h. We will write a small y as capital Y plus a constant k. Now when we differentiate a small x and small y, we simply get differentiation of capital X and differential capital Y, because h and k are constants which we will decide. So here it will become d of capital Y by d of capital X is equal to, and when you will see here, we have substituted small x and y by capital X plus h and y by capital Y plus q. So when you will do the substitution of small x and small y in these four places, you will come across an equation a1 capital X plus b1 capital Y plus a1 h plus b1 k plus c1. This will be the numerator. What will be in the denominator? a2 capital X plus b2 capital Y plus a2h plus b2k plus c2. This is what we have done here. Now what happens here, that the numerator is having x and y term, and there is some other term also which we want to make it 0. If we successfully make this term as 0 and make this term also 0, then this will change into homogeneous differential equation with a linear degree in the numerator and linear degree in the denominator. So a1h plus b1k plus c1 is 0, a2h plus b2k plus c2 is 0. Now if you see this carefully, this is a pair of linear equations in two variables h and k. These are the variables, and a1 b1 c1 a2 b2 c2 are constants. So if these equations are true, then you will get a solution of this pair of linear equation, which will give you a value of h, a unique value, and a unique value of k. Why this is so? Because we have already taken that a1 by a2 is not equal to b1 by b2. So here, if a1 by a2 is not equal to b1 by b2, we have studied in pair of linear equations in two variables that it has a unique solution. That unique solution is the value of h and the value of k. Now if you take that value of h and k, then this will be 0 and this will also be equal to 0, and you can proceed with the normal process of homogeneous differential equation. And in the end, when you will get the answer in capital X and capital Y, just substitute capital X as small x minus h and capital Y as small y minus k, and h and k are the values which you have obtained after solving these pair of linear equations. So this is about reducible to homogeneous differential equation. I hope you understood this part. You can take any example and you can try it. There is no issue with that. Let us come to the another form which is called linear differential equation. So linear differential equation basically is of the form, this is linear differential equation, and it has various forms. First, the most common form is that we write dy by dx plus py is equal to q. So what is p and what is q? Let us see here. So in a linear differential equation, what happens, that p and q which we are using here are either constants or function of x, any function of x. This can be another function of x, this could be another function of x. So in that case, we have an integrating factor which is e to the power integral of p dx. When we do this part, what happens? We multiply this on the left hand side and on the right hand side, and the left hand side will become e to the power integral of p dx into y, its derivative. And similarly, we will multiply on the right side, it will become q into integral for e to the power p. If you want to confirm, there is no problem. Here just apply the product rule. So what will happen? First term, which will be multiplied here, into derivative of y, dy by dx, plus second term, which is actually y, and the derivative of e to the power integral p dx. So when you will integrate, when you will differentiate e to the power integral p dx, one term will be e to the power integral p dx, because exponent on differentiation gives again an exponent multiplied with the derivative of this. Now when you will differentiate with respect to x, this is actually integration of p, and then you are differentiating it. So eventually you will get p. So what is happening? Then when you will write e to the power integral p dx here, e to the power integral p dx here. So this whole term can be written like this, and the right term is as it is. Now when you do this, what will happen? That you take this dx on the right hand side and then write derivative of e to the power integral p dx into y is equal to, this will go on the right hand side, q into e to the power integral p dx, and integrate both the sides. Now on the left hand side, the work is not difficult, it is very simple, because what is happening? Integral of a derivative. So this derivative and this integral will cancel each other, and you have already got a term here. Here you have to do the integral, but it is only a function of x here, because p is also a function of x and q is also a function of x. So overall this is a function of x and its integral, where you have to apply indefinite integration. Let me take an example here which will make it more clear to you. So let us take that we have dy by dx plus sin x into y is equal to x. So dy dx plus py, p is sin x, which is a function of x. Here a constant could also be there, but not a function of y. Here it is also a function of x, or a constant could also be here, but not a function of y. So our integrating factor over here will be e to the power integral p. P is sin x dx. When you integrate, you get e to the power minus cos x plus c. You don't have to do that. In the end, we will do all the plus c's once. So this, when you will multiply with e to the power minus cos x, this also will be multiplied with e to the power minus cos x, and this will also be multiplied with e to the power minus cos x, which is the integrating factor. So the left hand side, you don't have to do a much of work if you remember the theory. This is actually derivative of e to the power minus cos x into y with respect to x. If you want, you can check. This is e to the power minus cos x derivative of y plus y, and the derivative of e to the power minus cos x is e to the power minus cos x into its derivative, which will be minus of minus sin x, which will be plus sin x. Here you have multiplied with this x into e to the power minus cos x. In the next step, let us multiply this dx over here and integrate both the sides. Here the task is very easy, y into e to the power minus cos x. Here always you will get y into integrating factor. This you have to integrate, and the best way to integrate is by parts. So when you apply by parts over here, what will happen? Obviously first function is x, Eilert rule. So first function, integral of second is e to the power minus cos x, or we can Eilert, yeah, the integral of e to the power minus cos x we need to have. So but one thing is, actually integral of all the functions is not possible. So I think e to the power minus cos x will pose some problem. So let us do one small thing in the question which I have given. Let us take it as x into sin x. This was actually q. Okay. So we will take here x into sin x, which is q here, and then we proceed. So first function is x, and second function is all of this. So integral of e to the power minus cos x into sin x. So I'm doing this orally. You will integrate by substitution. You can take minus cos x as t, and its derivative is sin x dx, which will be dt. So e to the power minus cos x into sin x after integration will give you e to the power minus cos x. Okay, minus integral derivative of x is 1, and again integral of e to the power minus cos x into sin x, which will be e to the power minus cos x dx. So we have come to integral of e to the power minus cos x. So similarly, we have to proceed in linear differential equation, and finally, if this is integrable, you can integrate it. Otherwise, leave as it is if it is not integrable. In questions, the function will be given which can be integrated. So the overall process is this, that we multiply with integrating factor both the sides, and then after that we proceed, and the left hand side becomes easily integrable, exact value will come, and right hand side, by the knowledge of indefinite integration, you can integrate. There is another form of linear differential equation which says that dx by dy plus, earlier we took dy by dx. So this is nothing but we have reversed the role of x and y, plus p dash x is equal to q dash, where p dash comma q dash are functions of y or constants, but not x. So p dash q dash are functions of y, there p and q are functions of x. There was y here, here we have taken x. There it was dy by dx, here dx by dx. So here integrating factor would be e to the power integral of p dash dy. All the roles have changed, just interchange the role of x and y. So integrating factor is e to the power integral of p dash dy, and this integrating factor multiply both the sides. On the left hand side, what you will get, you don't have to think a lot, e to the power integration of p dash dy into x. On the right hand side, q dash multiplied with e to the power integral of p dash dy, and then integrated. There also we were doing like this, here also we are doing like the same manner. Here only y and x have changed their roles. Third form of the differential equation is actually Bernoulli differential equation. So there also there is some adjustment which we have to do, and finally it will be reduced to linear differential equation. So what we have to do in Bernoulli's differential equation, there is a name given to this. On the basis of that concept, you can make any other reducible to linear differential equation. So dy by dx plus py is equal to q y to the power n. So it is similar to linear differentiable equation, only difference is that here y to the power n is multiplied here. So what will happen? Let us divide by y to the power n on both the sides. So this is 1 by y to the power n dy by dx plus p 1 by y to the power n minus 1 is equal to q. So 1 y will cancel. Now we can substitute, let 1 by y to the power n minus 1 is equal to t, this term. Let us suppose it is equal to t. When we will differentiate both the sides, we will get minus n minus 1 y to the power the term minus 1. So you will get y to the power minus n dy, and there you will get dt. So you can easily say that 1 by y to the power n dy is equal to 1 upon, let us absorb minus, so 1 minus n dt. So 1 by y to the power n dy can be written as 1 upon 1 minus n dt. So after doing this substitution, what will happen? This equation will change into a form which is dy by y to the power n can be written as 1 upon 1 minus n and dt by dx. Another term is p upon y to the power n minus 1 and 1 upon y to the power n minus 1 is t. So this will be plus pt, and on the right hand side is equal to q. So this is now a linear differential equation. You don't have to worry about 1 by 1 minus n, because 1 minus n will multiply here and here. It is simply a constant. So this is a linear differential equation in t and x. dt by dx plus a function of x into t is equal to a function of x. So instead of y, here t is there, and then you can proceed by taking integrating factor, and the integrating factor over here would be e to the power integral of p. P will actually become p into 1 minus n. So 1 minus n is outside p dx. So this will be the integrating factor of this one, and then you will multiply both the sides and proceed. So this is about Bernoulli's differential equation. You will come across many other differential equations which can be changed into linear differential equation by doing substitution or some other manipulation. Now we will come across the last topic, which is orthogonal trajectory. So if we have been given an equation, suppose x square plus y square is equal to r square, and we all know that this equation is equation of a circle with center at origin and radius r. Since it is a family of circle, radius r is the arbitrary constant. We did in the first lecture also. We differentiate and finally we get dy by dx is equal to, if you remember, minus x upon y. This was the differential equation corresponding to this. I want to get orthogonal trajectory of this family of curve. What do you mean by orthogonal trajectory? I will just explain it to you. So first task is that we have to differentiate this and eliminate all the parameters, arbitrary constants, and write a differential equation. After that, we will change dy by dx by minus dx upon dy. The reason being, we want orthogonal. Orthogonal means perpendicular. Now this is the slope of the tangent, and this is the slope of the normal, and normal is perpendicular to tangent. So if we want the orthogonal trajectory, we don't want the slope of tangent, we want the slope of normal. So instead of this, we write the slope of the normal and put here minus dx by dy is equal to minus x by y. Let us see what we are getting, then we will understand it geometrically. So minus minus will cancel, dx upon x is equal to dy upon y, integrating both the sides. On the left hand side, you will get log of x, on the right hand side log of y, plus some constant. Log of x is equal to log of y plus constant, and finally you can take log of x upon y is equal to constant. Log x minus log y is log of x by y, and x by y is e to the power constant, which is another constant. So x is equal to ky, where k is a constant of integration, an arbitrary constant. So x is equal to ky. So the orthogonal trajectory of this circle is actually a straight line, x is equal to ky, where it is passing through the origin because there is no constant added to it, and it is having a slope 1 upon k, y is equal to 1 upon kx. Now if you remember, all the circles having center origin and any radius, this family of circles, if you find a orthogonal trajectory, that one, that is actually a family of lines passing through origin, infinite. You can take any circle from this family of circle. You can take any line from this family of line. And when you will see the intersection of both of them, let us take, this is the circle which we have selected, and this is the line which we have selected. The points where they will intersect, this point or this point, they are actually perpendicular to each other, because this line is nothing but normal to the circle, because it is passing through the center of the circle. So orthogonal trajectory simply means that for a curve, you are getting an orthogonal trajectory, means that all the family of curves belonging to this equation is perpendicular to all the members of the family of this curve at their point of intersection. So in order to do this, what you have to do? You have to first differentiate, eliminate the arbitrary constant, substitute dy by dx with minus dx by dy. This is the main step. Put here, don't substitute here, only dy by dx. No xy will be touched. And then again integrate and find the equation in the normal form, no differential. So this equation is an orthogonal trajectory of this equation. So differentiation, eliminating arbitrary constant, getting a differential equation, substitute dy by dx by minus dx by dy, and then again go for solving the differential equation. So this is all for differential equations part 2. I hope you have understood. And if there is any doubt, we will see. Thank you, students.